Mostly yes. Good. Turn these things on. All right, so we've been talking about screening designs, and namely, the last thing that we've been doing was exploring how to do some follow-up runs. So projectors are coming alive. There we go. So the idea here is in screening designs, the whole point of it is they're messy, but they're messy because we're not doing a whole lot of runs. So what we'll be doing is after we finish a screening design is we're going to be doing some more experiments in order to clear up the situation if needed. So I've jumped back, I think, a couple pages in notes just to review the example we were talking about. Everyone here, page 35. Okay, so we were looking at this situation. We had this reflected design, and so initially we studied 7 factors in 8 runs. Remember this? Does this at all look familiar? Okay. So 8 runs. That was a 2 to the 3rd base design. So you write a full factorial in those factors, and then you add factors D, E, F, and G. So D, E, F, and G, and you add them by confounding them with various columns in the base design. So that means that for 8 runs we have 7 factors and a mean, so there's nothing more we could really do to saturate this design further. So we're trying to get a lot out of these 8 runs. We run the experiments, no replicates, and we calculate effects at the bottom of those columns. And the first thing that we notice is, oh, it looks like factor A is doing something. And remember, even though this says factor A, it's A plus all this stuff. Actually, and more. These are truncated. Right? There's a lot more interactions, but it's just giving us through 3rd order stuff. And you can set that in Minitab what it will give you. So very realistically, we know 2-way interactions can happen. So this A could be due to the main effect of A. It could be due to the BD interaction, CE, FG, or even some combination of any of those. Is everyone okay with that? The idea of confounding. And we see B was also standing out as pretty big, and same with F. So B and F. And we went through this last time. And I asked you, keep an eye on this D, something strange happens there. So we had 3 effects that seemed to stand out from the rest, A, B, and F. When we analyze this, you make a half normal plot. This is a full normal plot, Pareto diagram. And you see these 3 things are seemingly the significant factors. And because you've got 3 main effects, we ended last class talking about, well, that's sort of makes you worry a little bit that there's an opportunity for a lot of 2 interactions between these factors A, B, and F. So more runs is sort of warranted because we don't know really what's happening. Is this the main effect of A? Is it these 2-way interactions? We have these guiding principles that would say our first interpretation would be A, B, and F, right? The main effects of those guys. That would be what our interpretive guidelines would tell us. But it's not saying that it's always going to be true. The factor for B could be this 80 interaction. We don't really know. Does that make sense? Okay, so more runs. If we think this is our interpretation and we'd like to clear that up, one way that we could do this, we've been talking about that, would be to do some more runs to break out the main effects of A, B, and F and sort of break that confounding pattern right there. So get A, B, and F clear, and then leave these guys lumped together. And if A, B, and F still stand out to be significant, then that's great. We've confirmed our interpretation that we have just the main effects of those three guys. So the one follow-up run that we know is called the fold over or the reflected design. And what we do is we take, here are 8 more runs, and if you look at this and compare it to our original 8 runs, which was that, we take in every 1 and -1 and just flip the sign. Does everyone see that? So these are all have the signs flipped from before. And so that is called folding on all factors, and that breaks the main effects from the two-way interactions. So when we look at this, we see factor A gives minus 47.5, which is pretty good agreement with what was happening in the first 8 runs, right? And B, we get minus 67. We compare it to here, we had minus 43. A bit of a difference, but they're still big things. F isn't too far from where it was before at minus 25. But then the surprise was D was insignificant before, and we flipped all the signs, and now D turns out to be a pretty important factor. So that's a surprise, and so we need to take a look at why that is, okay? So now let's look at a little bit more detail. So these were the design generators that we went over already. That's for the first 8 runs. When we flipped all the signs, you can go back and figure out, well, these design generators, you know, this design generator D is still going to look like D equals AB before, but flipping the signs, we have a negative out there. So that happens there, and this you can take a look at when you flip the signs A, B, and C. When you already flipped A, B, and C, the G generator stays the same. So you can see G is still A, B, and C. So this design generator stays the same, but don't worry too terribly much about that. So we have the 2 design generators for the first 8 runs, second 8 runs. So from them, we can get the defining relation, right, from the design generators. So we take those, we have I equals ABD, we have one term for each of these, then we start multiplying these guys together to get all of these contrasts. And we've only shown, some of them. Is everyone okay with the defining relation in the first 8 runs? So why can we flip the signs? What's that? Why can we flip the signs? Why can we do this, flip the signs? Sure, you can run any experiments you want to, right? So if you think of, this was a what, 2 to the 7 minus 4 design? So we ran 8, so what is that fraction then? 1 over quarter 8, 16, 1/16? So we're running a very small fraction of the runs we could have run. We're just adding, these are more runs that we didn't include in the initial 2 to the 7th design, right? So from that full factorial, we ran a few up here. We're just saying, well, let's grab these down here that we didn't run and add them to it. And we didn't go in a lot, but that idea of when you flip the signs, what happens is, what I'm showing now is it breaks the confounding from the main effects to the two-way interactions. So the first 8 runs, we have that defining relation, and as an example, I said, okay, A is confounded with these in the first 8 runs. If we look at the second 8 runs, that's the defining relation, and A is now confounded with the same things, but a different sign. So that means in the first 8 runs, here it is, so A and the BD interaction are adding together, right? The number at the bottom of the A column is due to A plus the BD effect and others, right? Here, it's the bottom of the column is the A plus the negative of the BD effect, right? So if the BD interaction was, say, plus 10 here, it'd be minus 10 here. So that is why we're doing this, because when you put those things together, when you say, here's the first 8 runs, here's the second 8 runs, and we put them all together, right? So if we add those two, we got this result in the first set of 8 runs. We got this result in the second set. When we add them together, that's due to twice this number right here is due to twice the A effect. And notice what happens here. Those things cancel, right? Whatever the BD effect was contributing to this one, it was doing the opposite here. So if it was adding 10 here, it was subtracting 10 there, and therefore it's canceling out. So we end up with 2A equals that, or A equals minus 50.5. And so that is clear of 2A interactions, right? They've all canceled out. So the purpose of this is just to show you, oh, when you flip those signs, this happy thing works out. This happy circumstance, those 2A interactions cancel out, and now we've broken free our main effects. So the main effects are clear, and we still have the 2A interactions lumped together. So notice, just looking at this some more, if we just take our first 8 runs, that's the first set, and there's the second set right there. And if we just lump them together and calculate effects like we normally do, you do get the answer that we just showed by going through this explanation of what's happening. So now when you look at, if you take that whole set of 16 runs, the first set of 8 runs, the second set of 8 runs, and say, what is the confounding pattern of the design after we fold it over? Notice this thing. The main effects are only confounded with 2A interactions. The 2A interactions are still confounded with themselves. And we've got one guy that's just a jumble of higher order interactions. So what resolution is this? Main effects clear, 2A interactions confounded with themselves. Right, 4. So what happened is we went from initial set of 8 runs was resolution 3, and we added 8 more runs. It's now a resolution 4 design, and the main effects are clear. So now our interpretation will be a bit easier. Now when we look at the full after folding, we have A, B, and F that are significant, as we suspected before. The A-B interaction popped out as significant, but keep in mind, you have to be very careful with this. When you do this, even though Minitab will just list its AB, it's all these guys, right? So this is AB plus CG plus EF, and we have to figure out which of those 2 interactions is doing something for AB. Yeah, Aiden.
Why is it resolution 4?
Why is it resolution 4? Because the main effects are clear and 2A interactions are confounded with each other. Does that make sense? And before it was resolution 3, main effects and 2A interactions were confounded with each other. So here's a couple questions that we first have. We got the same results as the first 8 with A, B, and F main effects, right? We got some new results, new significant effects. AB interaction turned out to be significant. Let's see, okay, so AB is significant, and it wasn't in the first 8 runs. So let's compare what happened. In the first 8 runs, where in the world was this AB interaction? It was confounded with what? So where did it show up? Ooh, here we go. In the first set of 8 runs, where's AB? You guys have already told me. It's there, right? It was confounded with D. So in the second set of 8 runs, so it was, we had this number down here. This was this 4 I told you to keep an eye on. So AB is significant in the, we found out by adding runs, AB was significant. We also found out D was significant when we did all 8 runs, right? So why didn't we find it there? That's right. There, someone mentioned over here. All right, thanks. So some of it, so Derek mentioned over here that look at the effects of D and AB, right? So way down here. So D has a strong negative effect, right? So when you increase D, whatever it was, the whippability went down. When you increase AB, the whippability goes up. And in the first set of 8 experiments, the confounding was this. So that means both these things changed the same way. That in the experiments, when D increased, so did AB. And their effects were opposed to each other. D was trying to decrease the whippability, and AB was trying to increase it. So when you add it together, they canceled out. When we folded it over and we broke that apart, then we were able to see D having its strong effect separate from AB, and then the AB's effect having its strong effect. Does that make sense? And by AB, it could be any of those. So we would say we have A, B, hardly read these things, D and F as significant, those guys. And then this, we need to interpret that. Our interpretive guidelines then tell us what? If you had to pick, and you do really have to make some decisions as to what you think's happening, of these 3 two-way interactions, A, B, C, G, or E, F, which one do you think is really the significant one? A, B. Great. Why A, B? Right. Okay. So significant interactions usually come from significant main effects. So the AB interaction is an interaction between 2 variables with significant main effects. So we would take a stab or guess that AB is the one that is the significant two-way interaction. We don't know for sure, but in general, that's the way we would go and move forward. So the next step would be we could take these 4 factors and run a full factorial with them. We might already have that when we drop the other factors, probably not in this case, but the next step in our design would be, let's look at these 4 factors, let's run a full factorial, then we'll get all the two-way interactions between them, without confounding, and after that we will do our center points, which is what we started this whole business with, right? Full factorials and center points. We'll do center points, test for curvature, and then go from there. Any questions about that? All right, so before we go to there, I'll hand some stuff out. Let's go through this case study together. Here, I want to pass that down. Start passing that one down this way. You guys work this one up. Okay. Let's look at this. So this is a real example. Couldn't ask for a better one. Really couldn't. It's exciting. It's chemical engineering based. That's not why it's so great. It just makes it better. Has everyone got one? Two more. Is there some extras here? Thank you. Okay, so I'm going to read through the situation. Excuse me. Okay, everybody read through the problem? So these guys built a new chemical plant, and now they have problems with their filtration unit operation. And why do you think it's a problem that the cycle time is high? Why do you think they're concerned with that? Lowers your efficiency. Define efficiency. It does lower. There you go. So lower. So we would say throughput, right? So apparently they don't tell you all the details, but apparently the filtration step has now become the bottleneck of your plant. So if you're looking at any sort of process, and I'm talking chemical process or manufacturing process, debottlenecking is things that engineers do. And that means that you look at all the stages, all the steps in your process, and one of them will be the rate limiting step. One of them is holding up the show. And so when I worked at Coke, it was the welding cell. When we were making stuff, when we were manufacturing column internals, getting things through the welders was the holdup. So you try to adjust your design so you didn't have to make things that were welded. So anyway, debottlenecking would be, all right, we've got a plant, we've got some process. Where is the slowest step? Right? Slow, they're all going at the same rate. We know that, rate limiting step. You guys should know that. And so what is the slowest step, which means what is the step holding up the show? And right now, in the old plants, it was something, we don't know. But we built this shiny new plant, and now it surprised us, the bottleneck is happening in the filtration step. So it's taking a lot longer than it did before, and so we had built this plant, we based all the economics on justifying building this plant because we're going to produce so much stuff. And now we're not meeting it. We're not producing probably anywhere close to how much we thought we were going to. So as you can imagine, everyone in this company is going to be looking at this problem. Right? You just built a large new plant, and it surprises you that you can't produce what you said you were going to produce. Okay, so that's a big problem. So now, so they go in and they get together with a bunch of people who, from the old plant, from the new plant, and figure out everyone who knows stuff about this filtration step, plus they brought in at least one of these guys as sort of an expert in helping them do these design experiments to figure out what's happening. And so they get together in a room and they say, let's come up with what we think is happening. So they think, what's the deal at the old plant? What's the deal at the new plant? So the source of water, they switched it from the old and the new, from town water to well water, or vice versa. And all these other factors were things that had changed between the old and new plant and could potentially impact the filtration time. Right? They probably had a lot of others, but they narrowed them down. And so I like that he mentioned that. There's a lot of disagreement in the group of, okay, what's important, what's not. So when you come up with this list and you've got then the different factor settings, then we need to test this. So expensive tests, run an 8-run design. Anyone have that appendix handy? Or did Matt does? Anyone else? Or did printing costs win the day? Okay, anyone find the table? Let's see if I can find. B1-5, that looks right. So when we find the right table, we're trying to find what? 8 runs and 7 factors, right? Now, are we going to use a Plackett-Burma design or a full factor, or excuse me, a fractional factorial? Fractional factorial, because 8 runs, that's a power of 2, so a fractional factorial is going to be much better. We probably don't even have a table that shows a Plackett-Burma in 8 runs, even though it exists. So there we have it. B1-5, it says, I don't know if I can do this. It says we have 8 run for 5 to 7 factors. This, right there, this guy would be our design. Is everyone okay with that? Know how to find it. And it tells us, doesn't give us the entire defining relation, does it? It just gives us some of the terms, and it gives us an abbreviated confounding table only telling us the main effects and two-way interactions. Right? There are a lot more. We just did an example of this, this level. Does that make sense? Okay, so next step, go and do the experiment. So let me see where we're at in this. I don't want to jump ahead. So what I ask you to do is tell me what the design generators are for this. So I probably haven't finished that yet. So what are the design generators? Think about how we put these together. When you have an 8-run design, you start with the base design, and then you add factors. So if you look at that, you can do this a couple ways to figure out how the factors were added. Make sure to work in groups, talk to people around you. One way to do this would be look at the defining relation and think of what are my added factors. And for design generator, I have to assign those to something in my base design, which has factors 1, 2, 3. This is what I've asked. This one is- Good for me. I'm glad I asked those questions. First of all, what's the run order? Is it this one right here? Would you run this experiment in this order? No. What would you do? Randomize. Thank you. Make you very careful with that. See if you can get the entire defining relation. That's a challenge for today. Do you have any extra handouts, or just? Just to make sure everyone's on the same page, let's talk about the design generators. Okay, so we have 8 runs, so it's 2 to the third. And let's do this. So the base run is a 2 to the third design. So that's x1, x2, x3, right? That's the base design. And then we have to add x4, x5, x6, and x7. So we need a design generator for each of those 4 factors. There it is. So that is the base design. And we need a design generator for x4. So what is x4 confounded with? So x4 is confounded with something in the base design. One way to do it would be just to look at the pluses and minuses in the x4 column and back it out, but that might take a while. Another way would be to look at this confounding pattern here. Or, even better, go down one more and look at this defining relation. Does this give us any clues what x4 was assigned to? All right, there we go. So, and think of, in terms of the base design, which is factors 1, 2, and 3, that term has to come out from, we assigned x4 to the 1, 2 interaction. And that's going to give us this in the defining relation. Can you see that? So 5. And you can come up here and you could say, oh, x4 is right there. And the 1, 2 interaction, you multiply that times that. Okay, that makes sense. 1, 2 interaction is that. So you could check if you wanted to through the columns. x5. What was x5 assigned to? Right there. 1, 3. Going to give us that term. x6. 2, 3. x7 was what? All right, the 1, 2, 3 interaction. Those were the design generators. Yeah.
Now, if you're like thinking that your number four factor was gonna be significant, would you wanna like, put it with the 1, 2, 3 interaction, so taking that
Oh, yeah. Yeah, that's a good question. So if this laundry list of 7 factors, from your discussion, you probably have an idea of which things are important and which ones you just put on there just in case. And in those cases, you do have a choice in the confounding of sometimes you can say, oh, this main effect seems to be a little bit clearer interpretation, not less confounded than the others, depending on the design. So in that case, you would probably try to fine tune it and have that one as clear as possible. So that's a good question. But even so, even if you did what you're talking about, look at factor 7, it still ends up being, in this case, confounded with 2 interactions. But sometimes, you're right, sometimes you do have a choice where a main effect you're pretty sure is significant, you can tweak it to make sure it has the least worst confounding. All right. So those are the defining relations. And this is a 2 to the 7 minus 4. It's a resolution 3 design. And what fraction? We just said before it was 1/16, right? So how many terms should be in this defining relation? We should have 16 of them. We have, and remember we count this one as a term, we have 5. So that's what you're after now, to try to get the rest of the confounding pattern. And to do this, we talked about this before, is we take these terms and we just start multiplying them together, right? And we do them in all possible combinations. So what I would suggest, if you have to do this on an exam, I would say, all right, I'm going to multiply them all together in pairs. And I'm going to keep track. 4 choose 2. So what's that? 6 terms? So I should get 6 terms out of that. Then I'm going to multiply them. I'm going to take them in groups of 3 and get 4 more. And then I'm going to multiply them all together. 4 terms taken 4 at a time. And I'll get 1 term out of that. So there's my 11 more terms. So we can just start doing that. We take this times this. We end up 1 squared, 2, 3, 4, 5. Then these two. 1, 3, 4, 6. 3, 4, 7. Is that right? And we move on, do that one, and then do that one. So let's work through that. 1, 2, 5, 6. You guys getting those answers? Make sure you can get those, get the rest. If you have questions, let me know now. Yeah. What's that?
I don't understand that.
Okay, that 4/2 was back in chapter 2 or 3. We said how do you make combinations? So we have 4 terms, not I, and we're gonna multiply them 2 at a time. So that's 4 choosing 2. So how many different ways can we take 4 terms, multiply them in pairs? And so that's the number of combinations formula. So we should be able to get 6 terms by multiplying them pairwise.
Gotcha.
Then when we multiply them 3 together, we should get 4 more terms. So if you don't do this, you're going to be hopelessly lost. And even if you do this, you're probably going to be lost in this case. done the easy one. I've done the pairwise. If you don't know what we're doing, make sure to ask me now. If this doesn't make any sense.
Why is it
Pardon?
2 factorial, 2 factorial?
Oh, it's this factorial times that minus that factorial. I can write out this. It's that combination formula. I shortcutted it here. So this would be 4 factorial divided by 3 factorial, 1 factorial. And this would be 4 factorial. So it's just this bottom guy and then the difference between the top and the bottom for the other term. John. Yes.
So what if we have like a 3 and 3? Have 1.
Then you'd have a 3 left.
Okay, so
Yep.
it's all literally this.
Right. Good question. Okay. So everyone done with multiplying, or at least got the idea of how we're doing that? At the end of it, I'll give you I won't write them all down now, but at the end I'll give you the full answer for that. So, all right, let's move on to the next part of this. Kind of what's happening. So if you want to start passing that around. There you go. If you want to pass this up. Okay. There we go. Second page. And you, second page. Sadly, there's nothing in there. All right. Okay. And again, keep in mind, this is a real situation. Need some extra. Bonus one. What was the resolution for this one? 3. Good. So main effects confounded with two-way interactions. That would be this comment on the confounding. So, I took this straight from the Box Hunter and Hunter text, so if the passive voice drives you crazy, like it is doing to me, I guess we'll blame them. You okay with that? Passive voice? Don't like passive voice? Don't use it in your reports? Good, good. That's a good start. right, so then they did the 8 experiments and got the results, sat down as a group and noticed, right away, hey, these filtration times are really short, and they noticed what, A, C, and E. It's when those things were high. When all those 3 factors were high, filtration time was really short. So again, as kind of bears out in the case study, there are going to be certain people, so they blames management here, which probably appropriate. The people most on the hot seat for getting the plant going and working fine would say, all right, we fixed the problem. Take these 3 factors, set them at their high values, and let's run the plant that way, and then just move on. Right? And probably at some point, if this plant is operational, they probably did that right away to try to see if the problem was fixed, or at least to get the throughput higher. Okay. But now, what we're after, and what you want to try to press more as an engineer, is, okay, that's fine. It's kind of like a Band-Aid. We did some experiments, and we'll just take these settings. But what we're really after is if you can understand what's happening and why, then we have a greater potential for really solving the problem. So we make this distinction between fixing and solving in this case study. Really solving the problem and then actually helping us in future designs and other plants and so forth. So, so everyone see, okay, filtration time was down significantly in those 2 runs. But what we're trying to do now, how would you analyze these data? To figure out, we've got certain effects. These aren't effects, right? Those are runs. The effects are right here. So how would you determine which effects are significant? All right, I'll let you go through this. And go ahead and go through this in the group, and then we'll get back together. The last one's the fun one. I will give me 4 interpretations that are reasonable in the last one. 4 different interpretations, if you want to be redundant. Oh, wow. It's sad to look at the clock and find it's 9:51, just when we're getting started. Sorry about that. It's over. But we'll come back and we'll do some more of this tomorrow.